Okay, hi. So I'm John Heidemann. I'm here from University of Southern California. And this talk is a little different than the other talks you've heard. Rather than talking about a specific system, I'm going to be talking more generally about research and the research process. And I hope to be having some discussion with you. So we'll see how that goes as we go along. So thank you for having us at this lovely location. We got to see much of it yesterday. And I was so inspired by all of this old stuff. Although it's not really that old. But it's old for us Americans. I wanted to talk to you about Plato, because I'm not going to try in Latin, but I'll talk to you about Plato. So Plato has this allegory of the cave, which some of you have probably heard before. It's a story in one of his books, much older even than Ireland. But he talks about how there are these prisoners chained against the wall, and they can't see the real world. They can't see outside. They can't even see behind them. They're stuck against the wall. All they can see are these shadows on the wall, and the shadows are cast from these objects that people hold next to a firelight, right? They're not even shadows of real things. They're shadows of these objects that people walk around. And then he uses this to illustrate and discuss with Socrates, I think, what is real, right? What do people see? What happens when these people maybe become unchained and go out and look in the real world? How do we perceive the world? And you know, this is Plato, right? The guy who gave us the Platonic ideal, the shapes and stuff, you know, and he's thinking big thoughts, and this is 2,000, 4,000 years ago, something like that. It's a very different world. But I think this is kind of interesting, perhaps, to think about. What does this mean for us as researchers? What does this have to say for us? So in this talk, so there we are. I want to have some discussion. And so my first question to you is, does this allegory mean anything to you about your research? So as networking researchers, what is our cave? Do you identify with the objects or anything in this? So I've got time.
Maybe Ripe Atlas is a cave.
Ripe Atlas is the cave? Because we're all stuck in there? So let me see. I don't know why you're picking on Ripe Atlas. Did email leave? In the back there? I'm sorry, I don't know most of your names, so.
I think we can use the shadows as the measurement we can do to the internet of the real world as the actual device we cannot see. So we are like studying the shadows to infer what are the real stuff. I don't know if it's very clear.
Yeah, I think that's one way to read this analogy in the context of internet measurement, right? We're trying to imagine the real world, but we can't see it, right? Any other suggestions or comments?
So for me, the cave where the prisoner is, there's a lot of times which mistake that I have done too is look at a problem, specifically measurements for me and maybe for other researchers too, is to start with a preconceived notion of what the result should look like.
Mm-hmm.
And by that, I'm already chaining myself and only looking at one-way perspective.
Okay, yeah, I'm sorry, I don't have my bullets, but yeah, that's an interesting one, right? Are we stuck thinking about what it is we expect as opposed to what might be real? Yeah, that's a good one. Any other thoughts?
So maybe the objects see as the ground truth that we like to.
Yeah, an interesting question in this is the ground truth the objects, or is the ground truth the stuff outside the cave? I don't know. That's something to think about. There was one over here somewhere. No.
So the cave would be the trace route tool, and the shadows basically the output of the trace route tool, assuming that the packet took this path, when in reality it was not one packet but a lot of packets.
Yeah, so that's an interesting one. I'm going to come back and talk about that specific example with traceroute later. Traceroute's an interesting thing, and it is kind of elusive. So,
Yeah, I would maybe would like to introduce another question. What are the persons that we think of the internet?
what are the persons?
Yeah, the persons.
You mean the people holding the objects? Oh, that's a good question. I didn't think about that. What do you have an answer to that?
Well, maybe some agencies that want to manipulate the traffic or hide something. I don't know.
So you used the word manipulate. I'm going to change it to manage. I mean, it's interesting. There's a lot of people who care a lot about the internet. Some of us care a lot about it after the last U.S. election cycle, or that was bigger than the internet. But there's definitely people who want to manipulate it, and not just for political purposes, but who's the I don't know who the local telco is, but Telefonica and Verizon and all these companies, they want to manipulate the internet to optimize their profits and to maximize their customer base. Yeah, so that's interesting. Anyway, any other comments? So I'll have a little bit more to say about this, but before that I wanted to say a little bit more about the internet. So, there was a time when the internet fit on a napkin or on a piece of paper, and this is a picture of the internet in 1969 when it was just getting started. But those days are way beyond us, right? Way in the past. And today you see things like these, right? This is in fact, this is more than 15 years old. This is the cable and wireless network around the year 2000, or the map, the Cheswick and Birch data that Kata plotted of. So this was nominally the entire internet, except to plot it. This is actually a spanning tree of the entire internet. So it's like you take the internet and throw most of the links away to get it to not overlap. And then this is the census survey data that we've done a bunch of, where we try to probe all the IPv4 addresses. So it's a long way from 4 nodes to this stuff. And that's one of the challenges as we measure it. One of the challenges that is as we look at the cave or the shadows or imagine the objects. Let's see if this works. So from my point of view, when I was thinking about this internet, this analogy, I was thinking of the researchers as being these people stuck here with limited view. And we can measure some things, but we measure them imperfectly. We only see the shadows. And yet we want to make inferences about the actual objects that are casting those shadows. And I kicked around for a while what outside meant. And we had different comments here. But to me, the outside is not necessarily what is directly here, but it's what maybe could be, maybe what should be. And I do hope, as we do research, we don't think about just measuring what Telefonica or what is a local telco? I'm sorry.
Aircom.
I'm sorry?
Aircom.
Aircom?
Yeah.
Or Aircom or whatever, cable and wireless, or pick your poison. We shouldn't just think about what those are doing today, or the people who are manipulating things today. We should think about what we want the future to be. If you think about Plato and his imagining these perfect solids, we should imagine what should the perfect things be that we want the internet to be. So those are my thoughts in the context of this analogy. So for most of this talk, I'm not going to talk about Plato. I'm going to talk about some different kinds of experiments. But before I get into those case studies, I wanted to talk a little bit about what we want to see, what we want to measure. So I wanted to ask you, that's going to be a problem. I wanted to ask you, what do you want to measure? What kind of research? So I've seen some of your posters, but what other things? So I guess, what did I see in posters today? So we were measuring recursive resolvers, right? And how DNS resolvers are selected. And I saw a couple of people were mapping trying to do anomaly detection using different kinds of techniques, right? I always have trouble spelling anomalies. Anyway, what kind of research are you guys doing? Are you most interested in? In the back?
Discovery of subnets on the topology.
Discovery of what? I missed the important word.
The subnets and then the
Oh, yeah. So that's a really good one. Can we discover the structure of the internet, right? Are you looking just in the address space, or are you actually looking for the mesh, the routers and links?
both.
Okay.
I start from the prefixes and then I try to reconstitute the structure.
That's right. I saw your poster the other day. Okay, any other comments from people, things we're looking for? There's a room full of networking researchers.
Congestion?
I'm sorry?
Congestion on links?
Oh, yeah, that's been a recent thing of interest, right? Not just on links, but also exchange points and things like that. Yeah, that's great. Any other suggestions?
Database monitoring.
What did you say?
Database monitoring.
Database monitoring?
Mm-hmm.
So databases are kind of general. What do you mean by that?
So what you can do is that you can observe the queries and you can find not the anomalies but queries with malicious intent.
So you're like looking for malicious queries in URLs and web requests, or?
No, directly accessing sensitive information without needing to know.
Okay, so I'm going to say in applications over the internet. Okay. It's an interesting question. IMC, for example, has sometimes struggled, I think, with how far is the internet. If it's the Internet Measurement Conference, does it go all the way into the applications? And they've had different views over different years. Any other suggestions?
Measured deployment of new features.
Yeah. So the comment was deployment of new features, right, as technology marches forward. That's a really important one. I've been trying to look at IPv6 recently from different aspects, but there's lots of new features. That's a hard one to measure too, but many of these are hard to measure. Any other comments?
Can you add deployment of new bugs to that as well?
Deployment of new what?
Bugs.
Oh, bugs, yes. Yeah, exactly. And an interesting thing, so I was involved in trying to add privacy to the DNS. And it's a really simple idea, right? Can we just put DNS over TLS, right, and just go home? But the pushback we got over, well, there's resolvers out there that won't be happy with this. It was huge. So measuring these things is critical, right? So I'm not quite sure how to say that. It's not new features. I guess it's sort of constraints. And you can think of it as a bug, but understanding those really holds up technological progress sometimes. Okay, any other comments? One from over here.
Performance measurement of protocols.
Performance. So we had congestion. What kind of performance do you mean?
Like application layer or transport layer protocols, like web protocols.
Yeah. Well, let me call that as different. Yeah, so performance, it's just a silly thing. So like quick versus TCP is one example. Yeah, that's a big deal. Can we make things go faster? Okay, so we have a pretty big range of stuff here. Let me think. Let me see. Let's just do this. So from my point, I had divided things up differently. I had topology down. Oh, I had size, because I'm a lot about measuring how many hosts there are, stuff like that. But I did have capacity, which is one of the things that came up. There's a bunch of things about applications. We had talked about one, but also things like quality of experience was in a couple of posters, and that sort of ties in. That's one measure of performance to look at. And we didn't say much about reliability, although we said bugs. And congestion is kind of like not reliable. Anyway, so there's a bunch of things to measure. And the real challenge is most of these things are fairly opaque. It's fairly hard to get your hands on these, right? Okay, so another way to look at this is there's a bunch of research topics with different levels of maturity. And we can take all the things on the last slide and then think about all the ways we measured. Some of these things you heard about in the last 2 days, right? I think, did I put RIPE Atlas up explicitly? Yeah, Atlas, and you heard about some aspects of the CADA work the other day. So there's a lot of tools out there. I think the thing we didn't hear about maybe is test beds. So Planet Lab is still around and still does some unique things, although Atlas, I guess Planet Lab's a lot more flexible than Atlas, but a lot smaller. The other thing we didn't necessarily hear, on the first day we heard, I missed it, but there was a mobile app, right? That was sort of one of these platforms that sits on devices and lets you do things. And I think one of the posters was about something you can put containers on, I think. Another way to get code out into the world. So there's a lot of ways to get hands on this. But what maybe there's not so much about is ground truth. And the real focus of this talk is to hopefully encourage you to think about what ground truth means. And from my point of view, ground truth is about defining what is correct, right? If you're going to measure something, you always ask the question, did I measure it correctly? And so how do we know what correct is, right? And one thing, if you could take away anything from this talk, I hope you take away this idea that there is always a correct, even if we don't know what it is, right? Right now, there are some number of people in Ireland, and I don't know how many it is. I don't even know very close to, what is it? 10 million? 4.5
million.
4.5 million.
Yeah.
But I flew in yesterday, right? So it's 4.5 million plus one.
Yeah.
You know, we never are going to know exactly how many people are in Ireland because some people on a boat that just went out to sea. But that number exists. There is a number. So it's important to think about that. And it's important to think when we talk about how many people there are in Ireland, to think about how precisely we can make that statement. Because did I just fly in or not? I don't know if the census keeper is keeping track of that. Anyway, so one way to look at height, one way to look at ground truth is to think about something simple like height, right? And so my height might be 180 centimeters, although that's sort of approximate, right? Because we could get a laser, some kind of fancy laser measuring device and get it to like 180 point something, something, something. But is that really my height? Is that a true, correct view of my height? What's the challenge with that? What's the limitations on even this super precise number?
Well, then there's, at some point, you can't measure any more accurate.
Okay, so there's limitations, which I can't spell apparently. Yeah, so we can get out my super laser measuring thing and get it to 3 decimal places, but there's atoms in there and there's molecules. And, yeah, so that's a limit.
You're taller in the morning because it's
yeah. Yeah, so my height actually changes. It's sort of like Ireland. People come and go. My height changes over the course of the day. So maybe it doesn't make sense to get my super laser device measuring out because an hour later I'm going to have a different number. Yeah. Any other thoughts about true measuring of height?
The definition of a meter isn't really.
Oh. No, we have a solid definition of the meter. It's so many transitions of some wave, something.
Is that constant?
Yeah. Well, the physicists tell me it is. Only the kilogram. The kilogram is sitting in Paris. That's all we have for a kilogram. But people are working on that. Any other comments? Yeah, so to me the biggest thing is this one. Height changes. So even if you're, you know, some super duper physicist with super precise instruments, not so well defined. Let me see if I can do this correctly. No, that would not be correct. Oh, yay. Okay. Yeah, so for me, that's the biggest issue, that height actually varies. And I looked it up. It actually is plus or minus a centimeter over the course of the day. So actually measuring your height more precisely than a centimeter doesn't really make a lot of sense. So let me ask you, though, so if we have this fundamental problem, which is height is limited in how fast how precise, or if height keeps changing, what should we do about this as scientists? So I try to figure out how to, I've lost focus on my window. Oh, darn it. So how do we fix this imprecision? Let me go in the middle.
Some parameters or
Have some parameters, what do you mean?
like for example, for the height or your bends.
We could have our height and our what?
Bend even the height of if you are inclined or something.
Oh, yeah, because I
Yeah.
have to stand up straight when I take
Yeah, parameters.
Okay, so we could think about defining
Parameters.
height parameters carefully. Anyone else? Any other comments? Let me see over here.
Define an average, for instance.
Yeah, how would I define my average height?
You could measure multiple times, for instance, in the morning, before sleep, or during
Yeah.
the day, and then some measure.
Yeah, and so we could not just define, we could compute and report an average. Yeah, that's a good idea. Anyone else? Did I forget? Yeah, let me go over here.
And sometimes we're forced to explicitly state that our research is only for a specific snapshot in time.
Yeah, that's a good one. We could say we only took heights at 2:30. Yeah. Anyone else?
Define an error rate and accept your true is.
Yeah, so that's kind of like defining an average, sort of. An alternative is to define a number but report error bars, right?
Mhm.
Yeah, good. Anything else? This is pretty comprehensive, I think. Yeah, so I think you got everything I was thinking of. Let me see. So I had the time thing, and I had the range, which I think is sort of a combination of what you both said. I think both of these are important. Both of these are reasonable. I will say, do you guys have any preference between the two? What do you recommend? What was the other ones you had? I think, yeah.
I would go with the range.
You would go. Why would you go with the range?
Even if you define parameters and you take an average, a stats guy is going to come along and say, no, you should have taken a median.
Yeah, the statisticians are pretty obnoxious about that. Any other thoughts? Preferences?
There is a problem because the signal is not stationary.
Yeah, so that the underlying data is not stationary, right? So she's already using the fancy statistics word, you can tell.
It's really an issue.
But that doesn't matter, right? We still have to get a number. I still want to know how tall I am.
Something which is not stationary.
I'm sorry?
It seems to be nonsense to go to the mean on something which is not stationary.
But I gotta know how tall I am. I'm gonna buy clothes. So, but we had some alternatives, right? She suggested that we report an average over the day, right? Does it make sense to report an average that's not stationary, of a value that's not stationary?
No, yes, we should not do so.
You should not use it at all? Okay. I mean, that's an option. So one.
Yeah, it must be taken into account. You must be cautious about that.
Just a second. So, I mean, that is an important, that is a perspective, right? And you do have to be very careful. I think caution is very important.
You have to be careful.
But we got to do something because I don't want to be naked up here.
You have to do something, but maybe consider that it's
yeah. So if we consider my very practical problem, that I don't want to be naked up here, you know, if we think about clothes, you know, they're not like form-fitting. So there's a little bit of leeway here. So maybe we don't need to be completely accurate, even though my height changes, right? So I give me some air bars or something. It's my preference so that I'm not naked up here. But anyway, another comment?
Yes. The point. So shouldn't we clarify why you want to measure height in the first place?
Oh man.
Because it makes a difference to measure height for
Yeah, that should have been on my slide. That's a really.
Or to maybe use it as a biometric feature for access control, right?
That really should have been on my slide. That's a really good comment, which is you should ask not just what height you're trying to measure and how precise you should, and should you get out the laser calipers or whatever, but why are you doing this and what is really important. If you're trying to judge, am I taller than my children, you don't need to be very accurate. If you're trying to measure clothing, you need to be more accurate, but you maybe don't need to know if it's 2:35 in the afternoon. Yeah, and that's a really super important comment. Why are you doing this? How much precision is needed for what you're doing? And in fact, I see a lot of papers that report numbers to like 5 or 6, 10 decimal places. That's just silly. That's where you shouldn't be doing it, right? Because most of those decimal places don't mean anything, and you don't need them for the purpose that you're using. So anyway, any other comments on what we should do here? So I think the one point I would come down hard on is, so while I respect the point of view that we maybe should be careful about and not do things that we can't do, rather than just saying not to do it, I think it's important to reframe the question in a way that we can do it rigorously. So I shouldn't claim to measure my height to 5 decimal places, but if I claim to measure my height with error bars, that I think is both honest and lets me buy clothes. So anyway, let's see if I remember the right combination. Okay, so from my point of view, and this says the same thing a little bit more complicated or more fancy and uses more networking terms, right? Truth is often not one number. Many things in networking don't have one answer. And if you want to give a rigorous answer, you have to accept that there's a range of values. And one example from my history, my prior work, is TCP performance, right? TCP performance is a huge deal. There was for around the year 2000, TCP friendliness was a big thing, and even today, people are still arguing about TCP and different variations of it. And I was doing work on NS2 at one time and was asked and took on the task of trying to validate TCP. And we actually compared TCP and NS2 against TCP in the testbed, right? So which do you think was correct? I'm sorry? Neither?
What is correct?
Well, yeah, what does correct mean? Somebody's been watching the talk. I mean, what was surprising, we expected to prove the simulator was correct against the real implementation. What we found is the real implementation got horrible performance because we set the buffers wrong. And because the testbed network was kind of funny and had, ATM links at the time that had weird buffering and stuff. So to me, a really important thing in networking is oftentimes there's not a single answer, but you have to think about having an envelope of truth, a range of answers that different systems have. And we need to think not just do we get an answer in that envelope, but when we present our papers, we should talk about what is that envelope, right? What is, today there's 800 million hosts in the internet, but what, does that change overnight? How much does it rise and fall? Things like that. And this actually matters a lot, right? So I gave you the example about validating the NS2 implementation of TCP, but there have been multiple PhDs about TCP friendliness and designing new congestion control protocols. That all hinges on what TCP performance is. And there continue to be people building new TCPs or people building new not TCPs. So, okay, so that's a little bit about truth being more than one value. So let's move on to these case studies and talk about some examples. So before we do that, though, I wanted to ask you, so where do you get your ground truth from? Where do you, this always goes back. There we are. Ah, don't pay attention to that slide. So where do you get ground truth from?
DPI.
I'm sorry?
DPI.
DPI? For what kind of, for what's your application?
For traffic classification.
Yeah, how's that working out on that encrypted data for you? So DPI is great. It's very invasive, but it's not perfect because of encryption. Any other places to get ground truth?
SNMP.
I'm sorry?
SNMP.
What are you trying to validate?
The congestion traffic measurements.
Okay. Okay. That'll give you a number.
Friendly network operators.
I'm sorry, I missed that.
Friendly network operators.
Yes. That's really important.
Is that a thing though?
Do they exist? Is that your question? Don't we have some in, where's Emil? Did he leave us? Or do you consider yourself a network operator?
No.
No, you're on the research side?
No, I'm also not.
Do you know any friendly network operators?
Yes.
Okay, they exist. Any other places to look?
Donald Trump.
I'm sorry?
Donald Trump.
He'll be happy to tell you some things. I'm sorry?
That's an environment that is completely controlled.
Oh, test beds. Yes, that's very important. So to think about these a little bit, so if you're going to get SNMP, I hope you've talked to the friendly network operators first. Another trade-off here, so privacy and invasiveness sort of is hidden here as well. So there's a lot of places I can't do DPI because they won't let me look at the packet payloads. And there's a lot of, and DPI stuff is sometimes expensive because it takes a lot of effort to look into the payloads. Even SNMP, maybe not just privacy, but also, what's the right way to put this? I want to say proprietariness. I can't think of a better way. Most people, you have to talk to your friendly network operators because most ISPs don't publish their SNMP data. They consider it a trade secret. The other comment was test beds. So test beds are really interesting. What makes test beds different than some of these other things? I guess you had the comment.
Because you completely control.
Yeah, so that's a really important fact. So if you completely control them, that's a good thing, right? I'm sorry?
Modulo the
Right, so there's both a good thing, right? You got complete control, so you can set up the experiment and don't worry about them screwing it up for you. But the bad thing is you have to model everything, right? You set up the experiment, so if you don't do it right.
Maybe unrealistic assumptions.
Yeah, so you have to know the assumptions. Or the parameters. Okay, good. So that's a bunch of places. Those aren't quite the same as what I had. I had the network operator down. Those are good. And I had test beds down. I had simulations too. Maybe that's because I did simulations a long time ago. Although simulations are arguably just another step along the testbed continuum. The other thing you can do is you can often look at prior results, right? You can see what prior published work says. So let me say a little bit more about that. No, not that key. We'll start here. So the first case study I wanted to look at was this idea of topology mapping. And this is something people have done a long time. Some of the really early papers are up here from USC, from University of Washington, and from UCSD CADA. And this is a map from probably before your time, but it was one ISP, mapped it a while ago. So how do we get ground truth on topology? Well, a lot of people turn to the operator. And if you look at these two early papers, they ask their regional networks, right? And got ground truth from that, or they ask ISPs to validate the results they found. So before we go back to this example, though, I want to go back to this question that almost came up earlier, which was defining correct. So what do we mean by correct? Right? I've said ground truth is what defines correct. But what do we mean by correct? It's obvious, right?
Something unambiguous.
Okay, so unambiguous, that's important. Wow, that's a hard one to spell.
Yeah.
Something that is acceptable for this experiment.
Okay, that sort of gets back to the comment earlier about what's the purpose, right? Something that fits the purpose of this experiment.
Yeah.
Anything else? I'm actually happy. As I looked at the posters, there were some, I saw multiple people using these kind of techniques, so.
Optimal?
Optimum? Wow, then I could ask, what does optimum mean? But
It means correct.
it means correct. Ah, now we're going in circles. You've got me in the cave.
You can use algorithms which have optimality results.
Yeah, so for algorithms at least, we can sometimes prove
Computation should be scalable.
yeah, hold on, I'm trying to think.
Prove that they're
You can sometimes prove optimality, prove that they're the best possible. Did we prove that you can't do sorting faster than n log n? Surely some theoretician is not.
No,
Sorry,
you
I'm not a
can't.
theoretician. I'm sorry?
There's better exponents than n log n for sorting, on average.
On average, sure. Anyway, let's not go there then, because that's not networking. And I lost, you said something else, I'm sorry, I missed.
scalable, but
Oh, yeah. So now we're sort of talking about nice properties of things, but I was hoping for something a little more concrete. If I want to say this is correct, how do I measure correctness? How do I judge?
I think that anything that have big lectures.
I'm sorry, what?
I think that everything that we have a big lectures.
We have big, I missed,
We have big lectures.
I'm sorry, I can't quite make out that word.
Just we have high probability.
Oh, big,
The most likely.
yeah. Huh, yeah. Maybe it has high probability of recurring, of being reproduced. Or being reproduced is probably the right word. Yeah, so that's part of it.
Something that can be compared to whatever the findings are. So actually know when.
Okay, but how do we compare it? So I'm trying to get at how do we compare it? Maybe the question's not completely well formed.
When we're looking at implementations, we can compare them to their design. and how they're specified.
Okay, yes. So, well, wait, but how do we compare implementations to the design? That's where the art is, right? Oh, I can't spell well, so let me give what I was thinking of was a lot more specific. So in particular, I really like the terms from information theory. And the technical terms of precision and recall and accuracy, which we'll define shortly, I think are really important. So what you folks had to say, I mean, these are sort of characteristics we look for in correctness, but ultimately I need to get this down to a number, right? You were talking about how we need to compare things, but how do we compare them? And the reason I like these terms from information theory is there's a couple of different aspects of correctness that I think are sometimes skipped over or not said clearly. So in particular, precision sort of gets this question of if I say something, is it true, right? I say Plato has an allegory of the cave. That's either true or that's false, and you can go look it up. Okay. On the other hand, recall is, did I tell you the entire truth, right? And I'm not a real philosopher, although I have one of those degrees, right? But I can't tell you everything Plato said, at least correctly. I can't tell you completeness, right? So my recall of Plato's works is very small. But hopefully I got that cave part right. And I think it's really important when we're looking at research results to make sure we don't just talk about precision, but also talk about recall. Because it's very easy to be 100% precise, right? I could tell you this network cable right now has no traffic going through it. My inference algorithm is 100% precise. But the recall is very low because I can only tell you about this network cable. And it's not even a network cable, it's a video cable. So I see more papers than I'd like that focus only on precision and ignore the recall question. Now, sometimes that's okay, right? If you're doing deep packet inspection and classification and you only want to classify certain things, maybe that's okay. But particularly when we're trying to do things like map the internet or understand the internet, its topology, its edge nodes, or map outages, I think we really have to strive to understand how complete our statement is. So to me, that's a really important aspect of correctness to think about. And then accuracy is a technical term that I'll mention briefly that sort of looks at both aspects of precision and recall at the same time. So there's a technical term from information theory, the confusion matrix, where you look at the truth, the ground truth that you have, and compare it to what your predictions are. And you start to talk about true positives and true negatives, right? Do I predict something's going to happen or that something didn't happen? And do I get it correct? And then you can define precision and recall precisely by basically looking at different slices through this matrix. So I think that's important to think about. So let's go back from this digression. We were talking about ground truth for topology discovery. So I went back and pulled these very old papers. Both of them talk about precision and recall, which is good. Both of them are very vague about what they have to say, which is not so good. The original, the Govindan and Brunkit. I know Hang Suda. She's a nice person, but long, hard name. Anyway, so they talk qualitatively about their work, and report precision and recall are high, but they don't quantify it, and they don't actually report numbers, which is kind of a shame. The rocket fuel paper, which was 2 years later, gave their results to ISPs and said, is this correct? What do you think, right? And they had some very specific questions. You know, do we see all the links? Do we see all the, do we miss pops? So they're looking at different aspects of the topology. And they actually covered both precision and recall. And they get sort of results, but it's sort of blinded because they only ask these yes-no questions, or these questions, and couldn't report actual numbers. And so there's this real challenge that if you're trying to test against a real network, which is, I think, what we'd like to test oftentimes, the data is proprietary. They're not going to tell you, and that gets in the way. Now, sometimes you can have a collaborator that works at a real network, and they can look under the covers, but you still walk away with these kind of qualitative answers. So, but the good news is, at least when I went back and looked at the original papers, they did look both at precision and recall, although they didn't use those terms. The other comment, we talked earlier about academic nets, and let's see, I guess it's the next paper. One of the later papers actually compared a bunch of academic networks. What are the good and bad things about comparing against academic networks? Let me see, peek ahead, no. Oh, now I'm in trouble. And this also applies to test beds, which was the comment earlier. Let me just fix this. So the Govindan paper compared against, what was it, Los Netos and CalREN 2. So CalREN is a California regional network, academic network. And Los Netos is an LA regional consortium. But other papers have compared against things like Internet 2 or Geont. Geont has a network, right?
Yeah.
And there was one other prominent one, I forget. Anyway, if we compare against these, so the nice thing about these networks are they publish topologies. It's open, you can compare. What are the disadvantages of comparing against these kind of networks? What?
They don't optimize for profit. I think. So
Okay.
do things differently then.
Yeah, so what the pro is that they have open topologies. So the con is that they're not, so maybe they're optimized funny, right? So they,
Only for performance instead of.
so maybe Geont tries really hard to stretch into those other 5 countries so that it covers all of them and they get the grant or something. I don't know that that happens here or not, but oh, shucks. So any other comments about that? Yeah, Eamon?
There's actually a paper, I think Tim Griffin, he called it GREN, and he compared it to the rest of the internet, and it's measurably different.
Ah, okay. I'm not familiar with that. So you're saying Tim Griffin had a paper on exactly this topic?
He calls it the GREN, Global Research and Education Network.
Ah, okay.
So it's different from the rest of the commercial internet. Well, these are the bits that I remember. So this is my
Sure.
Plato shadow of the actual
That would be a neat paper. Maybe you can share the site with it and I can stick it in here.
Yep.
So the other thing I wanted to pull on, we had this earlier comment about using test beds, and test beds are super important. But I think the comment that we had earlier there was that the challenge is you have to fill in all the details, right? If you fill in the wrong details, you don't necessarily get a right answer. So Okay, great. So that's about topology. I wanted to talk about another case study here. And the second case study is about edge addresses. So the research question is, can we identify all the active IP addresses in the world, right? Which IP addresses are lit up right now? And we published a paper on that in 2008 at IMC in Greece, actually. So what do you do for ground truth for this? Well, what we did was used our enterprise, USC. And this was neat because we had friendly operators. We at least knew who to talk to and could talk with them. Excuse me. The other neat thing is that we could actually bring multiple kinds of measurement to bear. So in addition to we were doing pings, right? We also did TCP probing. I think we nmapped the whole thing. And, oh, that was a different study. But we did TCP probing. And we also had passive traffic going into this network. And that actually turns out to be really important. So if you think about trying to measure which IP addresses are on at any instant, there's a lot of sources of error. And so, we have, nodes could come and go, right? People could buy a new computer and plug it in while you're doing your experiment. We did look at probe type, but the really challenging thing is we get overcounting and undercounting. And so we could have, there are some things that give us extra counts, like if you probe a router that has multiple interfaces, there's really only one computer there. Or you probe the broadcast address and get back a whole bunch of replies. But then we can also undercount because probes get lost, and there's firewalls. So that makes it harder to get error bounds in what we're doing. So the other challenge is that enterprises are not perfect. Even though we have friendly operators, USC is not a small place. At the time, they had 90,000 IP addresses, and management was decentralized, right? Some departments managed their own IP addresses. So nobody had complete information about which IP addresses were supposed to be lit up at any instant. And even when they had the information, like in DHCP logs, they wouldn't share that with us because that's sensitive, because DHCP logs, that's what the DCM, when we get sued by the movie industry because somebody's stealing a movie, that's the data they have to go after. So that's a very sensitive information. And even when they have knowledge, their knowledge decays over time because the world is changing around them. So the scary thing is, even though we talked to our network operators, they did not know how many addresses should be on. And they could even only give us weak guidance over, well, yeah, those addresses go to that building, those are DHCP and stuff like that. So what we did is define ground truth as all of the measurement methods we had put together as the best thing we could do. And we also called upon our network operators to try to check some of our assumptions, but that's what we end up with ground truth. And when we did our census of USC, we could then make statements like, we think recall is 62% relative to that number. Okay? So this is not a perfect ground truth. We'd like to do better, but it's what we had. The other thing we could do then is also look at other kinds of ground truth, like what happens if we exclude the passive data collection. So we had monitors at the edge of our university's network. We were capturing all the traffic that went in and out. So if we exclude that, we got a smaller number here, and we could judge how close we were to that, how good our recall was relative to that. And we get about the same answer, although not the same, right? So there's some envelope of truth here. Okay? So that's what we did in this case for our ground truth. And it was really advantageous to be able to work with the operators and to be able to get different kinds of data collection here, but it's still not perfect. Even with passive data collection, we never see things like printers that might not respond to our pings and aren't ever sending traffic out of the USC. So it's really hard to get ground truth. But you need to do the best you can. So any questions about that or comments? So this was good, but what's the big flaw with just studying USC? There's a huge weakness with just looking at USC, even though we have multiple perspectives on it and stuff. Anybody have a guess at what the problem is?
USC might have a different connectivity than other internet.
Okay, well, so we're looking at address liveness, but the key thing was USC might be different, right? Right, so what we would like to claim is these are the error bars on our measurement technique. But if USC is an oddball and maybe USC is super open, then that wouldn't be true. Okay. So the alternative we had was random sampling. So we took 1 million random IP addresses and used that. So what are the pros and cons of using 1 million IP addresses? Anybody?
Can you describe a little more what you did with the random sample?
Well, so we'll get that on the next slide. But what you'd like to do is, rather than just using USC, because USC might be weird, let's just randomly generate 1 million IP addresses, and then we'll judge, what does our measurement technique say? Is that address lit up? And in fact, the thing we compared is, does TCP probing, how does that look relative to ICMP? In the back?
The problem with drawing randomly IP addresses is that you don't know beforehand if these IP addresses are attributed.
Yeah, so a problem is we don't know if they're actually busy or if they're in use. Right, so we fixed that by probing with TCP and ICMP both and judging them both. And there was some, not overlap, some the opposite of overlap. There was some, the techniques were complementary. But yeah, the big challenge is, now we didn't know for USC if USC was really in use either, so we had to have all 3 ways of measuring there. But we know less here, right? So I guess another way is because we can't take traffic. Okay, so that's a big con. Any other comments, pros or cons? Nobody in the pro department, Moritz?
IP address space is not equally distributed, so random sampling.
Yeah, is that a pro or a con?
It's a con, I'd say.
So I'd say use of the IP address space. Equally distributed. So what's that going to do to our results? Why is that going to throw things off?
We might hit many IP addresses which are not in use maybe.
Okay. That's certainly true. Is that a bad thing though?
I mean, if you know how it's distributed, then it's not.
Okay. Well, so let's come back to that. Let's hold off for a little bit. Here?
It's not just use, it's also the distribution of the address space itself. I mean, like very, very long time ago, if you were a big university, you got a class A. Network.
So Emil's comment is that the part of the difference in use of IP address space is historically people got different amounts. I think the implication of that is, although, that it's just not uniformly used from this experiment's point of view. So, anyway, in the back.
There are also reserved prefixes. For example, this dot something is reserved for private use.
Yes. So that's a different kind of unequalness. I'll put it here separately. Yeah, so we filtered those out, I think. It was a long time ago. Yeah, so that's a different thing. So you guys are all haters today. Nobody wants to be in the pro column?
Well, I guess if you do it repeatedly, then random sampling is the best thing you could do.
Yeah, why is it the best thing?
Because you have no other ground truth. So if you were
Okay.
because you're trying to measure the
Well, we have other ground truth. We have USC. Yeah, that's two
which is
slides ago.
something that you don't want to use, right? You want something else.
Yeah. So I think, so anybody else want to comment about the pros?
There's no bias.
Yeah, so that's the one that's most important. That's why this is the best, right? So the key thing is a million things chosen at random is unbiased, right? It's by definition fair. And that's actually why the fact that the address space is unevenly distributed doesn't bother me so much. Because even though it's uneven, even though MIT got a /8 because they were here in 1980, so what? I'll get more MIT addresses for my random sample. So I think my comments were similar. So the unbiased is my biggest pro, and that's a really important thing. And the biggest con, I think, came up too, which is if I pick address 1, 2, 3, 4, I still don't know if that is busy or not. The part about uneven distribution is important, though. Large parts of the internet address space are not very fully used. So if I pick 100 random addresses, most of them won't get used, and I won't have a very good experiment because my population will be so small. That's a problem. But there was the comment that we can just repeat this experiment. We can do a lot of addresses to make that problem go away. The other challenge, though, might be maybe I care specifically about things that happen in weird parts of the internet. So there are parts of the internet that are mobile, what do you call them? Carrier grade NAT for mobile handsets. Those are like fully lit up /16s that all respond to ping. That's very different from a normal part of the internet, which is much more sparsely used. So you might actually care about sampling the weird parts, sampling the uneven distribution. Anyway, so let me push on. So we did this. We judged ground truth, as I needed to say earlier, by comparing the two protocols. We get a different number. We have a weaker ground truth here because we don't have this third method of passive observation, but we get a similar result. And so even though we got 3 numbers, and the numbers are off by a fair amount, right? 2/3 versus 82%, and now 74%. There's this envelope of, we're missing about a third. We're missing about a third to a quarter. And so that's the best estimate that I have currently of how much we miss. Okay, I want to move on to another case study, IP alias resolution. And there have been, this again was the problem here is when you're probing, when you're doing trace routes, right? You have routers that have multiple interfaces. How do you disambiguate when those different IP addresses all correspond to the same physical device and not pretend like you have two links? And the challenge is if I trace route through this, I could get responses that are from any of the IP addresses. Depends on how the router's configured. So there was some early work on this around 2000 from USC and University of Washington. And there's been a huge amount of work. So Kate has done a ton of work over many years on this problem, but other folks as well. So one technique to use for ground truth that's different here is because there's this breadth of prior work, you can actually compare against prior work. And so maybe you can get the prior code and run it, or maybe you can get the prior results and see if you get results and do better. And this is really good because we can actually show progress. We can show the world moving forward. But this can also be dangerous because errors can propagate. If one technique systematically missed a certain class of routers, we might never discover that those routers were missing. And this is why, again, I think even if you compare to prior work, which is important, it's important to also always try to find real ground truth, to talk to your network operators or do something to ground this in reality. And so I actually went back and looked at these papers. So actually some of the earlier work didn't actually validate the alias resolution part of the problem, because it was the first paper it validated the whole thing of did they discover the right topology. The spring paper actually compared against the Mercator paper, prior work. Recent work has gotten a little bit stronger, and let's see, so this compared against prior work. Some of these compared against academic networks. This is a CADA paper. And actually this paper, this Codex paper, compared against a bunch of things, although it actually did a bunch of other things in addition to alias resolution. So if you look over the literature, people use different techniques at different times. And some of these are in stronger places than others too, so it's a little bit more demanding. But comparing against prior work is important. The final thing I wanted to talk about, the final case study, is cable cuts. And this is a study I did with a student and Walter Willinger, where we were looking at this question of if you have undersea cables and it gets cut and a nation loses a lot of bandwidth all of a sudden, what's the impact of that? And if you remember a few years ago, there was like 6 months where we lost like 5 or 6 cables. There was one in Egypt that a couple got cut, and then this cable got cut off of, this is one of the cables that got cut just off of Singapore. So we have a tech report about this work. And what I want to say about it is it's super hard to try to answer this question, because if you think about trying to judge the effects of taking out a cable, you have to know what are the ISPs in that country, what is the traffic in that country, what is the application, how does the application involve. There's a lot of levels going on here, and yet we've got to have some kind of example, because I want to be wearing clothes while I'm standing up here. We need to make some judgments about how stable the internet is and how fragile it is in the response to big changes. So what I can say, what we did in this case, is use modeling. I shouldn't have gone to that. Just a minute. And I'm curious, what do you think are the pros and cons of using modeling? So we built simulation models of this at different levels and put them together. So we've heard some of these challenges earlier in the context of other kinds of ground truth. And maybe this isn't completely fair, because I haven't shown you the models yet. But any thoughts about modeling in general or simulation?
Simplify the problem.
Is that a pro or a con?
I mean, it could also be a con.
Yeah, so modeling is really fascinating. So it's fascinating because it simplifies the problem. On one hand, hopefully that means you pick out the right details. On the other hand, maybe you don't know what the right details are. Yeah, so that's really important. We'll talk a little bit more about that in a bit.
One point would be that you are comparing your result to what you think is sound, but it's also a problem, just like with the cave analogy, because it's the problem of having in mind a concept, but you don't know if that concept is true in reality. You don't know if it's true.
Okay, let me think about how to unwrap that. So were you casting it as a pro or a con first? Or both? Yeah. Oh, everything's both. So what you said is that I'm sorry, you're going to have to repeat it again. I'm having.
I was saying that if the pro is that you compare your result to what you think is sound and logical to your knowledge of computer networking. But it's also a problem because if you have something more exotic in the real world, you will consider it as something false while it's true in the neural network.
Yeah, so the first part of what you said is that it's neat because you explore the alternatives that you want to think about, right? And I think what you said about the con was that maybe, I'm using different words, but maybe the alternatives that you consider are not the right ones. Maybe you miss things. Is that fair? You see, there's a big risk that you have garbage in and garbage out, right? If you don't put the right stuff in. And this is something I think is in common with test beds, right? Test beds are very controlled, just like modeling. But if you put the wrong things in, you don't learn anything. Or worse than that, you learn the wrong thing. You learn something that's not actually true. Any other comments about this? Okay, so let me just to show from my point of view, so the part that didn't come up here, so a key challenge, a key benefit is you can look at lots of is that with modeling you can look at a ton of parameters, right? You can explore this huge space because it's just math, or maybe it's math plus simulation or something. And that's very powerful because you're not stuck just running one experiment. You can run lots of experiments. And there's this neat property that if all your experiments give the same answer, maybe you can prove something, or at least prove in the set of yours, prove in the context of the assumptions that you've made. The downside is, though, it can get very complicated very quickly. And there's this uncertainty. Do you have the right parameters? Which are things you guys said also. So just to show you what we found, here we are. So we had a multi-level model where we started from the physical layer and we worked our way up and looked at not just the physical layer, but the link layer, and then routing, and routing can adjust itself, and then transport layer and applications which can also adjust themselves. And it's really frightening because every level of this has parameters that can change. And not just has parameters that can change, but every level of the internet is self-adjusting, trying to do the best job it can. In the end, though, we ended up with graphs like this at the bottom, where we would graph based on how many flows there were. And by the way, we didn't know how many flows there were. We were looking at one country in this case. This is Bangladesh, actually. So we don't know how many flows went into Bangladesh. We think we knew how many fibers went into Bangladesh. And there was one, the one we were looking at, the one that broke was 20 gigabits, and we think there was another 10 gigabits into the country at the time. And so we could see, when we looked at performance, we were looking at quality of experience metrics. There's a ton of place where there's plenty of bandwidth for everybody. There's a ton of place where there's not very much bandwidth. And at least if we assume there are 50,000 flows, cutting this cable moved all of Bangladesh from having good experience to having horrible experience. And then we could also move this up and down. So if we think, oh, well, 50,000 is not the right number, if it's 100,000, we could get a different answer. So that was what we were able to do. So anybody want to throw stones at this? Because there's some real limitations to this. What are the problems? Eva?
So not like it's physical links, so you cannot sort of put them on one heap. Some people will have access to lightly loaded links, while others.
Right. So our assumption was there were only at this time 2 links in and out of Bangladesh, 2 international connections.
2 international physical cables.
Yeah.
That consist of multiple lambdas.
Yes, but when the cable gets snapped, all the lambdas go.
Yeah, but
So
there's still residential capacity.
there could be local capacities. So the application we were looking at was YouTube, which at the time Google had no servers in country. But you're right, these are all things we have to consider, which is there local servers able to handle capacity? Are there other links or other ways in and out of the country? And that gives us less certainty perhaps on this axis. Any other stones or gripes to make about this graph? There's sort of one big problem missing here, which is that if you have 50,000 people watching YouTube at a time and the link breaks and they're all unhappy, what's going to happen?
Less users.
Yeah, less users. People are going to defect. They're going to stop watching YouTube and they're going to go watch, I don't know, actual television. Yeah, and what that means is it's not fair to say we have 50,000 users all the time, even after this disaster to the internet. Actually, the line should angle down. And how much should the line angle down? How many people are going to give up and how many people are going to keep clicking the reload button? Again, it's a parameter we don't know. So the other thing we did was look at a whole bunch of what ifs, right? So I showed you this picture before, but we looked at things like, skipping ahead, right? So this graph is the what happens if you have defections, right? And we assume people go away after the performance goes. So we can guess at different levels of defection what happens. Alternatively, we can guess what would happen. We can do more positive what ifs, right? What happens if the country had double the capacity before we started? Well, then they start over here, and then they can maybe tolerate failures. Or what happens if they have twice as many, if YouTube is super popular? Well, then they're up here at a very unstable spot. So,
I have a question. Did you know for each cable how many flows went over that? Or
we did not have
total
ground
number of
truth
flows?
about the flows.
So it means it could be if there's two cables, that
Yeah.
one of them is used completely, one of them is barely used.
It
that
could
was
be, and we don't know routing, right? So in a sense, perhaps this is a futile exercise. Maybe there are too many parameters to reach a conclusion. We did the best we could. We tried to, at least when we didn't have ground truth, we tried to at least understand the space. So, any other comments about this or questions? So the bottom line is, I hopefully gave you a bunch of different ideas about ground truth, from like super strong, I can't spell, but super strong things like going and asking the operators and getting actual ground truth, to doing your best to model what's going on and look at a lot of different parameters. So just to wrap up, I wanted to go back to this allegory, right? We heard about that earlier. I had a couple other kind of fun things. So on one hand, you can think about, looking at the shadow, which is a shadow of some actual physical object. And then you can think about the object that, the ideal abstraction of that object, and you can think about the mathematical abstraction, right? The mathematical perfection, right? That's sort of how I imagine Plato thinking about this. There's also some things that I found. So we have that's a shadow, which you might recognize. There's a tricky thing, which is sometimes the shadow is actually cast from something that doesn't look very real. So this is from an artist in Red Hong Yi, who has a whole bunch of these. They're actually very cool looking. And then you can think about the actual object that might have been casting that, or that even though the object casting the shadow is not real, you can think about the object that inspired that, the object in the real world. Or, maybe you can think about the inspiration. And then the final example I wanted to give, so that's a shadow, right? Oh, I have an animation mess up here. You know what that is, right? Shadow of a cube. But that's actually a shadow of a hypercube, right? Although it's not a real hypercube because it's in 3 dimensions. The reality of the hypercube, my stupid animations, the reality is a hypercube is a 4-dimensional thing. And I think what's kind of cool about that is you can think about, this is a case where the shadow that we can measure, this 2-dimensional thing, which we can recognize, the thing that's casting the shadow is actually the shadow itself of this 4-dimensional thing that we can't actually see. But we can talk about these 4-dimensional things. And hopefully, as you're thinking about the internet and the internet might be, you can think about things like that that don't exist today, or that we can't have. So that's what I wanted to do to wrap up. So my encouragement for you is to always seek the truth. Don't just stop and say, oh, this is the best data we've got. That's good enough. I'll write my paper. I mean, I want you to write your paper, but be realistic about what the truth is and what you can say about the truth. Make sure you think about those different definitions of truth, and be creative about trying to dig into truth, because there's a lot of options out there. So we have a few minutes left for questions, but I know, well, otherwise that's what I have to say. So any other questions before we close? Everybody's tired. You did really well, because it's 2 p.m. is a horrible time to start this kind of a talk. Anyway, if not, I think we have our final poster session.
Poster session,
Yes. Okay.
Okay.